take you to this interesting simulation page. I don't know how many of you have aware of this TensorFlow playground. If you Google, you just type TensorFlow playground, you will get the simulation page. Okay. So we are yet to discover all these technical terms. Don't worry about all these technical terms. Okay, our course gradually we are going to discover all these terms. That is the objective of our course. In the left hand side, we have 4 different pattern. You could see, like, okay, in the top left we have like a circular pattern. This is something like a compartmentalized pattern, and this is one of the easiest pattern, simple pattern, and this is something like a Swiss roll pattern, isn't it? As we see different, of course, this is a classification problem because your data points are color coded. Whenever you do the scatter plot, okay, if every record has a label, obviously hue, you have to pass the label to get the scatter plot with color coded, isn't it? So by looking at the data, obviously it is a classification problem. So as we discussed, the challenge, when I draw the scatter plot in the whiteboard to the context of the regressor, but here to the context of the classifier. So when I draw the scatter plot for the regressor, you have seen some kind of a curvilinear pattern or highly scattered pattern, which makes you to decide, okay, it's having a nonlinearity, right? But here, to the context of classifier, you could see I have one set of records. Are spread over here. Another set of records are spread over here. I need to build a classifier, isn't it? If my data set is like this, even I don't require a neural network model at all because my data set is linearly separable, isn't it? What we call a simple linear model can solve this. A naive Bayes can easily solve this. A logistic regressor can easily solve this. I don't require a neural network at all. Let me run the simulation to show you how quickly the model arrives the training error and the test error near zero. Let me run the simulation. The moment I run the simulation, you just carefully watch this epoch number. Epoch number means it's iterative, because the model is going to work in an iterative manner. Even I'm going to talk about a gradient descent, okay, in the next session. But however, I just highlight about what is the gradient descent. Even you have used the linear regressor and logistic regressor. Under the hood, whether it's a linear regressor or logistic regressor, there also gradient descent is working in an iterative process. It's an iterative process. So once I present completely, imagine I have 100 training records. Every time I present 100 training records, my weights are going to get updated. Okay, once then again I represent the 100 records. Once again my weight get updated. Of course, there are different styles are there. We are going to discuss in detail what is batch training and all, full batch, mini batch, and stuff like that. For the initial level, just understand. Once I present my training records, my weight has to adjust. What are the weights? Weights are nothing but model parameters. Just like your linear regressor and logistic regressors, what are all the model parameters? When we say model parameters for the linear models, okay, y cap prediction is equivalent to beta naught, beta 1 x1, beta 2 x2, and so on. You write beta p xp. Okay. So what we call, these are the model parameters, right? What we call, this is the intercept and these are slopes. So when you extend this idea to logistic regressor, what happens? In the logistic regressor, I don't want to get this continuous, because this equation is going to give me the continuous numerical value. Okay, which span from minus infinity to plus infinity, isn't it? This range can go anywhere between minus, according to the values what you substitute, minus infinity plus infinity. But when I extend this idea to classification problem, I need to skew the output to the probability score 0 to 1. So what we do, we map this equation to the logistic function. So 1 divided by 1 plus e to the power is the logistic function, minus of beta naught, beta 1 x1, and so on, beta p xp. So that This continuous value, whatever you got, let me call this net in the neural network term. We are going to call this a net. This net, if I substitute in this function, I'm going to get the score somewhere between 0 to 1 to be considered as a probability score. That means what? This time your output is a class. Okay. Initially, we start our understanding with a binary class, then slowly we'll extend our idea towards a multi-class. So what is an idea here? What is the combination of these features? X1, X2, X3, and so on. X3 feature belongs to class orange, or it belongs to class blue. Okay. Assume that I have encoded all these blue data set as a label 1, all the orange data set as a label 0. Encoded like ones and zeros. This logistic function probability score, each and every record, it is going to give me the probability score to the context of label 1. To the context of label 1. I'm talking to the in the context of logistic regressor. I'm talking when we design the neural network, we have to do one-hot encoding to represent the output according to the number of classes. Okay. But when you design a logistic regressor or any machine learning model using sklearn library, okay, internally this one-hot encoding will be taken care by sklearn, but we don't explicitly do it. But when you design a neural network architecture, according to the output classes, we have to explicitly design one-hot encoding in the output. Even if you have 2 classes, your output layer should be encoded like this. Say, for example, healthy and cancer. Suppose I present a few records like X1, X2, X3, X4. These are all my features. So I have some hidden layers and output 2 nodes. Whenever I present a healthy record, okay, this node I will train for 100% probability for healthy record, 0% probability. This node. Whenever I present a cancerous record, these are all the features belongs to cancer patient. This time my output node should be trained for, the first node will be trained for 0% probability. The second node will be trained for 100% probability. That is how model weights are going to get adjusted. Which rule is going to, okay, what is the rule which is going to make this learning process? We are going to learn one by one. Okay, what is delta learning rule and what is the back propagation algorithm and all? That is the gradient descent rule is being adapted for multiple layers. That is the back propagation. Why there is no back propagation for logistic and linear regressor? Because there is no layers at all, just input and output layer. Look at this. This is an input layer and this is the output layer. Having said that, again, interview question. A neural network without hidden layer is nothing but what? You can confidently say it works like a linear regressor or logistic regressor. Understood? A neural network without hidden layer works as a linear model. Works as a linear model. Simply, it learns your input pattern according to the output node. It's a linear relationship. As the complexity increases, accordingly, I have to introduce the hidden layers. And the same gradient descent logic, when I extend it to multiple layers, there comes the rule called back propagation and all those stuffs. Okay, we'll be learning. So the moment I run the simulation, you see like how your traditional gradient descent learning is going to learn, same manner. Can you see there is a decision boundary and your training loss and the test error is almost is 0. No matter time. Look at this, even with less than 100 epoch itself, it reached almost 0. So there is no neural network requirement for this because it's a very simple record, right? So let me increase the complexity of the record. Look at the complexity of the record. The moment you look at this pattern, which model comes in your mind? The moment I look at this data points, which model strikes your mind?
Support vector.
Even simpler model?
Decision tree.
Yeah, very good. Decision tree. But yeah, support vector also can solve, but what is the idea behind the decision tree? Your decision tree will try to split the record. Say, for example, this is the X1 feature, this is the X2 feature. Okay. In the root node, all the records are there. First, it will split the record, okay, based on if X1 feature is above this threshold. Say, let us choose some threshold over here. All the record come to this side. Below the threshold, these guys will come to the left hand side. This guy will go to the right hand side, isn't it? First level. And here I'll ask the question: if X2 feature, if the X2 feature is above this threshold, you all these guys, you come this side. All you guys, you come this side. For this side also, this time I'm using X2 vertical feature, right? Y-axis feature. With the depth of 2, you can easily compartmentalize these records. That's how your decision tree works. But let us try to solve this using a neural network simulation. Let me run the same simulator here. Try to watch your output loss. Earlier, we have no matter time, we have reached 0.0, 0.0, isn't it? Quickly, we arrive the convergence. But look at the epoch is keep on growing, but there's no improvement that happened in the loss. It got stuck somewhere at 0.5. 50% of the loss only could reduce it. That means my neural network model behaved like a linear model, like a logistic regressor, could not handle this nonlinearity, isn't it? There is a nonlinearity. It's not a linearly separable. So what is the choice here is, let me stop this, okay, and I reset this, make it by epoch 0. I introduce the hidden layer. Don't worry, you are trying to understand in a bigger picture. You try to understand the logic in a bigger picture, then we are going to bisect into each and every minute details we are going to explore in detail. Okay. So what is the role of this hidden layer? Here, just you see, the moment I run this. See, the moment I introduce a hidden layer, almost another 25% to 30% of the loss has reduced. Earlier, it got stuck somewhere at 0.5, 0.5, training as well as the validation loss. Except a few records, okay, almost. Can you see this portion? These orange records are misclassified as blue, but originally they are orange. This also, because they are in the blue zone, they'll be classified as blue. Why they are classified as blue? Because the majority is blue. The probability of blue will be dominant in this zone compared to the probability of orange. Similarly, in the orange zone, the probability of orange will be dominant. So these blue will be misclassified as orange. Similarly, these blue also misclassified as orange. Because of these misclassifications, okay, still we have some error. But if I make my model bit complex in the sense more flexible, even I can avoid these mistakes so that I can make my training error almost zero possible. Once again, I reset this. I increase the number of computation elements in the hidden layer. Earlier, by default, 2 neurons. Now it's 3 neurons. Sorry, this pattern, right? I'm telling the line to bend little bit. Can you bend? Little bit. Can you bend? I'm telling the line little bit, little more. Can you bend? Hey, decision surface, little be flexible in the data points. Can you see few data points are little away from this line? Little bit, please bend, and adjust according to the data point. Earlier, your line was so strict, straight line. And the moment I increase the number of neurons in a hidden layer, can you see the decision surface? It's get tuned according to the data points. Still, your error has reduced far better than the earlier. the number of misclassified records is very less. Okay, even if I reset again, yeah. Now can you see we have a more flexible decision surface? Almost my training error and test error is almost zero. Okay, how it is doing is what we are going to discuss. And look at with the same level of architecture, if I go to little more complex data. First, obviously, definitely without hidden layer as a linear model, not at all possible. Look at this, like the same manner, your error got stuck at 50%. Definitely not possible. Now I introduce one hidden layer and try to solve it better than earlier. But still, these orange will be misclassified as the blue because they are in the blue zone. That is because of that you got around 29, 20% and 29 in the validation network. So to handle this kind of a complexity, what I do earlier with one layer itself, I try to increase the neurons. Now I try to introduce one more layer. Okay. So what is the strategy of increasing the neuron in the same layer or introducing a new layer? What is the strategy? First, try to see the result. Okay, then we'll deep dive into the strategies. Okay, I have to reset it. Reset and run. Okay, to make this process a bit quicker, okay, let me reset this and I make this to be big because I don't want to wait for too many iterations. With the 3 neurons, can you see I got a beautiful circular boundary very quickly. No matter time, it's less than 100 epochs. Your training error and test error. This also looks like your support vector machine. Whoever gone through support vector machine, this looks like your radial basis function kernel, isn't it? Your radial basis function is like a circular kernel, but but your neural network and support vector machine is sharing one interesting secret recipe, whereas other nonlinear model is not following it. Okay. And this is too complex again. Okay, here you required a few more hidden layers to solve it. Okay, you just play around with these simulator. You first initially you try to run with the default parameters. You don't need to modify anything. Okay, once you have traveled at least the 50% of the course, at least the end of the third session, once we finish learning backpropagation learning and all, again you revisit this. Then you can, by the time you know different activation functions, the role of learning rate, the role of regularization and stuff and all, you can play around with these parameters also. You can play around. So as you start manipulating with hidden layers and the number of neurons in the hidden layer, we were able to achieve the kind of solutions, whatever we were able to get, right? So coming back to the answer to the initial question I have asked, what is that one secret recipe the neural network is having when compared to other nonlinear models?
Hidden layers.
Hidden layer is the physical structure of the neural network to get that secret recipe to get it done. Understood? Hidden layer is just a physical structure to make that secret recipe. That itself, it's not a secret recipe. Actually, what it is doing with the data is what the secret. The physical structure of the neural network is enabling that process it is doing on the data set. So we are arriving to that point. Any guess? Let me put other ML nonlinear models in one basket. Other ML nonlinear model like KNN, decision tree, random forest. But I will not put support vector machine in this basket because support vector machine also it's like a brother and sister for the neural network. So it is also doing a similar characteristic of the neural network, but in a different way it is doing. It's a different way, but neural network is doing in a different way. But both are doing the same process. Another side, the nonlinear models like a SVM and a neural network. And in one basket. But the way in which SVM is doing it different. It follows the kernel trick. Okay, this one, the physical structure is different. As I told you, the physical structure, how SVM is getting the things done using a kernel trick. Neural network is getting the things done using multiple layers. Okay, using a hidden layer. This is the physicality of the model. What is the logic? Okay, this is the physicality. Okay, imagine this is like a wiring, hardware wiring, like our brain neuronal connections. This is something like a hardwiring. Okay, to make the wire work, I need a logic, right? Logic is something like a software. That makes the difference. Other nonlinear ML models, they can also solve a nonlinear problems and challenging problems. This is the tabular data set, which is a challenging tabular data set. So since we are learning neural network, let me talk to the context of the neural network. Neural network has the built-in dash capability to handle the challenging data. The challenging data may be linearly non-separable classification problem or a nonlinear regressor problem. What does that built-in? I'm talking about the logic. Okay. So what could be that factor? It has a built-in what capability do you think based on the simulation?
It works in iterations.
Yeah, it works in iterations. See, to be frank, and your logistic regressor and linear regressor also works in iteration. But working on the multiple layer. Okay, again, we are talking in terms of the physicality.
It is learning each feature very deeply.
Okay. Learning each feature very deeply.
We could see the clear distinction in the graphs.
Here you are tasting the final end product, Sahar. You are tasting the final end product and you are saying, so it's an awesome taste. The making process, what is interesting in the making process we are trying to discover. Okay, just make a note of it. To digest this idea, we have to travel till session. Okay. It is going to give a spark and it is going to make this neural network learning to be more curious the moment I mention this. See, these kind of questions definitely your ChatGPT will not answer, isn't it? So definitely your data scientist will be there. Okay, because of as soon as this day when artificial, the first software which is going to replace the data analyst, people are creating too much hype, but it cannot completely replace. Okay, it can support. It is going to be a support system only. Maybe an organization who recruit 10 data analysts, maybe they recruit only 2 human analysts. Okay, with the help of AI system, they are going to completely. They cannot trust on the AI system alone, because you need to guide properly those models. What to do? Still, an experienced data scientist is needed. These guys are working with the original representation of the feature. Original representation of features. And these guys, the secret recipe is, these guys are working on transformed version of features. You may wondering, sir, where does this transformation happens? The transformation is happening in the hidden layer. That means whatever the features you present x1, x2, x3, these features are being scaled by the weights, whatever these weights are going to learn with certain logic, and it is going to produce some intermediate output. Okay, these intermediate values are going to consider as a transformed version of this value. Whether this transformed version of this feature is solvable or not. So initially I have an input layer and output layer only without hidden layer. Then the moment I introduce a hidden layer, see, without introducing the mathematics again and again, I'm telling you, I'm just introducing the logical perspective. See, once you understand the logical perspective, understanding the mathematics is nothing for you. It's easy and cakewalk for you. Getting the logical perspective is very critical and crucial. Okay, I'm trying to establish that logical connection first. The once I introduce the hidden layer, what happens? Your input features or your raw features are being transformed as a linear combination of the input features. Say, for example, this output. How do I get? This is the first neuron of my hidden layer. How do I get? This one I'm getting as a sum of products of x1 weighted. X1 is getting weighted with the sum value, and x2 is being weighted by a different value. X3 is being weighted by certain value, and so on. As a summation of xi wi plus certain bias, you are going to get something. Of course, this is the linear in the sense, right? But if this transformation, if you provide just a linear transformations, you may not separate your features. So to push the data points to some nonlinear transformations, what we do, we give a nonlinear activations. What we do, once you bring a linear combination of x1w, x2w2, x3w3, x4w5, and so on. Say, for example, I have 5 features. So you have a linear combination of x1w1, x2w2 up to x5w5 plus bias. Okay, the role of bias is something like intercept. Okay, when I discuss the mathematics, you'll understand the importance of this. We provide a nonlinear activation. That nonlinear activation will push this value to some interesting transformed value between 0 to 1. What nonlinear activation we are going to apply over here is a sigmoidal activation. Only the term is new for you, but the mathematics is same. Same logistic function we are going to call it as a sigmoidal activation function. What does the sigmoidal activation function is going to do? It is going to push the sum of products of these linear combination of these values. It is going to push to 0 to 1 value. 1 divided by 1 plus e to the power minus of wi xi plus w bias. So w1, x1, w2, x2, and so on plus bias. You have a numerical value, right? That numerical value is being substituted over here. You get some value, something like 0.75. Here you got 0.65, 0.25, some value you get with a randomly initialized weights, right? Model will see, okay, now your raw feature is being transformed into these another set of combinations. Now these values are linearly separable or not. The output layer is going to work like a linear classifier. Between these two layers, there is no hidden layer, isn't it? Because this is treated as a transformed version of your x1, x2, x3, x4, x5 is being represented with this some new set of values, but a transformed version of these values. So instead of representing your raw feature with the 5 features, now I'm representing with some transformed version of transformed features. This transformed feature, your output layer, try to figure it out, whether I can separate this, whether I can bring a distinct probability score for this. Whenever I present another class, whether another combination of the value produced by this hidden layer, whether I can push the probability close to 0 for another candidate, can I push the probability score to 1? Whether this is not satisfactory, okay, we may end up with increasing more and more neurons over here, or sometimes one level of transformation may not be sufficient. We may end up with introducing multiple level of transformations. So each and every hidden layer is going to be considered as a transformed representation. For time being, please have an understanding of your neural network. It's working on a transformed representation of the features. Till the time your feature is being separated, okay, it's keep on transforming your feature, transformation to the transformation, transformation to the transformation, and so on. Finally, at one stage, your data you can visualize and yes, my data point could be separated at this level of transformations, or after two-step transformation, or after three-step transformations, whether my data is separable or not, your model will decide. So how we arrive that idea? From the loss function. Your loss function, you get a positive response like, okay, when compared to one hidden layer, my loss got stuck somewhere here, the gradient descent. Maybe with the two hidden layer, I could able to push my loss somewhere from 0.45 to 0.21. With the two or three hidden layers, still I can reduce the loss somewhere to 0.05. So you can understand, okay, my model is achieving a very good convergence. And there are different, fundamentally, you know only the gradient descent technique, isn't it? Gradient descent technique. Apart from the gradient descent, your stochastic gradient descent, there are some variations of those techniques are there. During your linear regressor and logistic regressor journey, you have learned a classical gradient descent rule, because these classical gradient descent rule you are going to apply on the linear models. The linear model, there is no challenge, isn't it? For the linear model, there is no challenge. That means your gradient descent is going to minimize the error in a very smooth manner. That means your terrain is very smooth. Why we call this the gradient descent? Because we are reducing the error to the descending direction. So the general expression goes like this. The change in error is directly proportional to, or I can say, what is our objective of any machine learning model? Let me make this point very general, not only the neural network model. What is the objective of, let me call it as my weights, isn't it? I need to adjust the weights. So the change in the weight is directly proportional to change in the error, isn't it? Change in the weight is directly proportional to the change in the error. What is the error function? In error function, I'm going to define the error function as y minus y cap the whole square. It's a squared error. What is actual? What is being predicted? Okay, what is actual? What is being predicted? You can treat the same function both for classifier as well as a regressor. Not a big deal. If it is a regressor, this y value is one hot encoded. Say, for example, at two nodes, when you are trying to calculate the two nodes, how this error is being computed is, say, for example, you expect 0% probability, 100% probability for a particular record, right? For a training record. But your model has produced 0.15, 0.85. How do you calculate the squared error here for each node? What is expected? Expected is 0%, 0 minus what is being predicted, 15% probability score, so 0.15 whole square plus what is being expected here, 100% probability, 1 is expected, but what is being predicted is 0.85. So the squared error idea you can extend even for the classification problem. Okay. Strictly speaking, of course, we are going to talk in terms of entropy formula, log loss. Okay. I will introduce when I teach the gradient descent in a proper fashion, when I introduce those gradient descent logic and how the gradient descent rule is being extended to the multiple layers of the neural network. Okay, there I will write the mathematics of log loss and entropy formula in detail. For time being, you try to generalize this error function. You can generalize this error function to the regressor. For the regressor output side, I have only one node, right? Since it is being a classifier in the output side, I have two nodes. So this node error plus this node error, I need to sum up. What is the error contributed for this, for a particular training record? Suppose assume that I have 5 training records. Record number 1, record number 2, record number 3, record number 4, record number 5. Okay. So this is for the error contributed by the record number 1, isn't it? Now the second record belongs to another class. Okay, so the target is actually the flip side of the target. That means this node I need to get 100%, this node I need to get a 0%. My second record belongs to another class. But what my model throws the output is something like this: 0.9, 0.10. Now I need to calculate the total error. Okay, what is the total error contributed by the total 5 training records? This kind of learning is called full batch learning. That means once you presented all 5 training records, my weight has to adjust it based on the total error. Or record by record, if you wanted to update, that comes under the stochastic gradient descent. So all the whatever the terminology I'm telling, we are going to talk in detail, okay, with a numerical example. Don't worry. Okay. As an initial session, I'm giving the complete picture about the entire agenda about the neural network idea, the logic, and the workflow, the mathematics bit. Okay. Now you assume the second record I presented. What is the loss associated with the second record? This node, what I expected is 100%, isn't it? So 1 minus 0.9 whole square plus this node I expected 0% probability. So 0 minus 0.10 the whole square. Similarly, the third record. Okay. You have something different square, fourth record different square, fifth record different square. You calculate the total error. So summation of the error once you presented the entire 5 records. So now see this error I got. Imagine this is before learning or in the middle of the learning. Assume it is in the middle of the learning. Who's responsible for this y cap? How I got this y cap? Y cap as a function of 1 divided by 1 plus e to the power minus of w1 x1 w2 x2. My weight has contributed. Okay, so my weight has contributed to this output. That means whatever the model parameters which is learned at this stage is enough, or still it required further learning or not, that is being defined by this rule, gradient descent rule. That is why we are writing is change in the weight is directly proportional to the change in the error. But something is missing in this expression. What do you think? Something is missing in this expression. Change in the weight. Of course, I need to adjust the weight to achieve better error. Better in the sense, what kind of error? Lower error, right? When, say, for example, this is iteration number 50. Okay, this score I got somewhere at iteration number 50. At iteration number 51, okay, definitely I'm looking for better error, right? So now put together this total error is somewhere here. Assume my total error is somewhere here. I need to bring somewhere little down, right? Then only I can say my model is improving. So what we call that?
Learning rate.
Yeah, learning rate I'm going to introduce in the formula. The W nu is equivalent to your initial W and contributed by this. Okay, this guy is going to provide the change to the existing weight. Okay, so whatever my initial weight or the early iteration weight, this guy is going to provide the change. So that change can be plus or that change can be minus. Okay, this guy is going to tell that, hey, you have to little bit high increase or little bit decrease the value, then only you can reduce the error. So in the general expression, what I'm going to write, your gradient descent rule is being defined like this. So what was missing in the general expression is the change in the weight is, sorry, before I introduce the equal sign, it is directly proportional to change the error. But the change in the error is in the descent direction, DSCENT, descent direction. How to mathematically represent the descending direction? The change in the weight is equal to minus of delta E. Okay, what does this minus sign indicate? It's a descending direction of the error. So how do we compute this? So what we call this is called as a error gradient. Okay, we call this as a error gradient. So you know this error equation, y minus y cap the whole square Okay, so this error gradient, we are going to write a change in the error by adjusting weight. So what amount of change in the weight will give a change in the error? That is what your error gradient is going to tell. So how do we compute this mathematically? Okay, that is the agenda. In the next session, we are going to learn this gradient descent learning, and we are going to apply that gradient descent learning, our very first model for perceptron learning. So what is our step-by-step learning process? Our step-by-step learning process, we are going to understand what is gradient descent. What is gradient descent learning? Okay, gradient descent learning. First, I'm going to apply the gradient descent learning to the ANN without hidden layer. Simple input output architecture without hidden layer. Okay. Obviously, this model can solve linear problems. And then I introduce a non-linearity. I'll introduce a non-linearity and I'll try to apply the same perceptron learning rule here. Perceptron learning. Your simple perceptron learning, when I call perceptron learning or simple perceptron learning, which indicates a neural network model without hidden layer, we are going to see that this perceptron learning is going to fail. It cannot solve linearly non-separable problem. Then what I will do, I will introduce a neural network with hidden layers. Whatever the outside picture about the hidden layer I have mentioned, I'll be deep dive into that. Okay, more mathematically, as well as I have given some intuitive understanding of the hidden layer in the form of a transformations. I will, in the next session also, I'll show some interesting simulation created by one of my favorite professors. So the two people I follow for my own personal upskilling and learning throughout my journey, the two popular personalities the leaders I follow in this field is obviously Andrew Ng, one of the world-renowned person. The second person, maybe you may not be well aware of. In fact, that person is one of the founding member of OpenAI, Andrej Karpathy. So these people work I closely follow. I try to update myself with whatever the new ideas, the concepts they proposes. One of the simulations proposed by Andrej Karpathy, one of the founding member of ChatGPT, I'm going to show that another interesting simulation to visualize how you can interpret the hidden layer. Even though you have seen this simulation, okay, but in this simulation, your final output is being mapped on the original feature scale, but you are not able to see the transformed value. It's not possible to see here, isn't it? Whatever the value is being, your input raw feature is being transformed with some intermediate values, right? If I take these values, if I do the plot, how that value works. So the next session, I will show that Professor Andrej Karpathy simulation page, the code is being written in the JavaScript. Don't worry about the coding. Let us work on the output alone, visualization. Try to comprehend the visualization. Number two, we are going to write the code on our own in the Python notebook. Okay, in advance, I have shared that notebook with you. Keep that notebook with you as a reference. Try to see, if you are more curious, try to see the steps, whatever I have used, implemented the perceptron learning without hidden layer. Just you play around with the notebook, but however, I'll teach you properly line by line. So with the support of Python coding, we also try to have some kind of a visualization technique. Of course, the lab 1 exercise without hidden layer, lab 2 exercise, I'll be introducing the hidden layer. So like the professor's Andrej Karpathy's simulation done using a JavaScript, we are going to visualize using the help of Python code. For the visualization, we can explore a lot of powerful visualization tools available in the Python itself, like Matplotlib, Seaborn package, and more powerful visualization is a Plotly. It's a three-dimensional visualization. You can do interactive visualizations. Using that visualization, I will demonstrate even much better interpretations, whatever you see in this. TensorFlow playground. So TensorFlow playground is the, whatever you see in the output is the final end product. That means once the records are being successfully classified, how it is being mapped in the output layer. That means how these records are being placed in the output with the color coding. But intermediate value, if I wanted to access, then only really you understand what happened to the original. Originally, the feature vectors are being placed circularly like this. After transformation, what exactly happened to those feature values? That is more interesting and curious to watch, isn't it? So that we are going to dissect that and we are going to understand. Not only logically and visually, also with mathematically. So I, as a pointer, as a quick pointer, I just given a very basic level introduction to with what equation we are going to start with. We are going to start with this error function. I'm going to introduce this 1 by 2 for a mathematical reason. I will tell you, when you try to derivate this dou E with respect to dou weight, okay, generally what we do in differential calculus, say for example, x plus 2y whole cube. This is Z. Don't worry. Okay, the mathematics, I will try to make it as simple as possible. This much level of differential calculus understanding is more than enough to comprehend the actual mathematics behind the neural network, whatever we are going to discuss in the session 2. Dou Z by, if I do the partial differentiation with respect to x, how do we write this expression? Whatever in the power you bring it to front, right? So 3 times of x plus 2y, and then I reduce the power by 1. And then we apply the chain rule to the inner term, right? X plus 2y. So whenever you differentiate this expression with partially with respect to x is considered as a variable, 2 is a constant, y is a constant, isn't it? So when you apply the chain rule to this inner terms, x is a variable, so 1, differentiating x is 1, plus 2y is a constant, so it is 0. So this is the partially we differentiate with respect to x. Similarly, if I partially differentiate with respect to y, what will happen? Dou z by dou y is equivalent to, bring the power in front, x plus 2y, reduce the power by 1, so power 2, apply the chain rule. Now, with respect to y variable, x is a constant, so 0 plus 2y. If you differentiate 2y with respect to y, you get 2. So this is the answer for dou z by dou y, 6 times of x plus 2y whole square. Dou z by dou x is nothing but 3 times of x plus 2y whole square. This much of calculus is more than enough to understand your entire mathematics behind the neural. Nothing more than that. Okay. So I will try to make this journey much easier for you. Okay. At the same time, more interesting with the help of Python notebook. So we are going to navigate into the subsequent chapters. As a quick summary, the key pointers, the first thing you should understand, what is a differentiator factor neural network when compared to other machine learning model is. First factor is neural network has the ability to handle unstructured data, of course, with its full capability. Full capability in the means the entire end-to-end deep learning architecture, which involves CNN layers also. As a foundation course, we are going to explore the classical neural network, which is going to play as a fully connected layer towards the end of the modern day deep learning architecture. We are going to explore fully connected layer as a multi-layer feed forward neural network architecture. That is what we are going to explore, which is having a special capability to handle the nonlinearity. Unlike other machine learning model, these guys are working on the transformed representation of the features, not on the original features. Even SVM also working on the transformed features. Okay, I will give an interesting example for SVM, how SVM kernel trick is working on the transformed features, not on the raw features. even for this neural network to comprehend the meaning of transform the representation of the feature, how a linearly non-separable problem becomes separable when you try to transform. The two important algorithm I'm going to touch upon is a Cover's theorem. What does the Cover's theorem is going to tell? That your original feature, which is not linearly separable or not solvable, it can be separable or solvable in the transformation domain. Okay, that's what your Cover's theorem is going to talk about. Okay, to validate this Cover's theorem, I'm going to give a very practical example, a simple numerical example, so that you can appreciate this process of transformations. So towards the end, okay, this is the hardware wiring, right? This is the hardware wiring. So what is the logic? The logic is gradient descent learning. How the weights are going to get updated. So the logic we are going to follow, the change in the weight is directly proportional to the decreasing direction of the error. So how do we calculate this error gradient? Dou E by dou weight. Suppose if you wanted to calculate how much of weight I need to adjust for W1, you need to compute this. How much of weight I need to adjust for W2. So this gradient score is going to tell, okay, finally you are going to get some number. Don't worry about the formula. The formula is going to involve, as Sahana mentioned, learning rate and stuff like that. We are going to see in detail tomorrow. Sorry, the next session. You are going to have something like, okay, minus 2.56 or plus 2.36, something like this. What does the score is going to tell? Okay, initially my previous iteration, my W1 have something like 0.76. And if my gradient score is going to give me 2.36, means what's going to do is plus 2.36. That means my weight is get adjusted from 0.76 to 0.76 plus 2.36. 3.12. So now the updated weight for W1 is 3.2. Similarly, my previous iteration W2 or initially my weight W2 is something else. By using the gradient calculation, we are going to have something, and this value is going to update the earlier weights. So how this gradient descent learning is going to learn the weights and update the weights? First, it is how it is working without hidden layer, and with the hidden layer, when it works, we are going to introduce the concept of error back propagation idea. Okay, so that is our learning path is going to go. So at every stage, we are going to see a lab exercise, different lab exercise. So we're going to validate our idea with, first, without hidden layer, we are going to see a simple perceptron model. Then after introducing a hidden layer, I will solve a multi-layer neural network model with hidden layer, how it solves. So once our complete mathematical understanding is validated with the Python coding, then from session 3 onwards, I will take you to work with some real data set. Okay. Particularly session 4 and session 5, we'll be working on the real data set. Primarily S1, S2, S3 is it's more focused on understanding the underpinnings of the complex neural network wiring. What is the logic? What is the mathematics? So the best way to learn the mathematics is to work with the toy data. Okay, I'm going to consider a small data set. You are going to see what are all the changes that is going on with these small data. Once you understand the logic, the idea, what are all the changes these guys are going through, obviously you can scale this idea to any realistic data set. The same idea is going to work. So this is how we are going to travel further in the subsequent session. I hope all of you have some prior knowledge in the Python. Throughout the session, I'll be working with the Colab based notebook. Okay, this is my Colab based notebook. Either you can work with the standalone Jupyter notebook, or if you wanted to work with the Google Colab, see, this is being a foundation course. Your free version of the Colab is more than enough. But if you move towards either computer vision application or large language model applications, obviously you may require a pro version. Because the pro version, you have a lot of memory in terms of RAM as well as the GPUs to handle the large volume of data. But for the foundation course, your free version is more than enough. So the benefit of using the remote server like a Google Cloud Server or Amazon SageMaker is you don't need to depend upon your machine hardware framework, isn't it? So you have to depend on your RAM space, or your hardware hard disk space, or even computational speed of your CPU. You don't need to depend on that. So you connect with the server, and another beauty here is you don't need to periodically update all the necessary packages. So all up-to-date packages will be available once you connect it to the cloud server. So that is why I also recommend all of you to follow Colab instead of using a standalone Jupyter, because moving forward for the larger projects, when you start building the later period of time, definitely cloud-based editor will